In today's webinar, we're going to continue with looking at the characteristics of photovoltaic systems, but more specifically the electrical characteristics. The IV curves, the effect of temperature on voltage and power, looking at series and parallel circuits, and starting to move on to the main topics for why people install solar and battery storage systems. So, on we go. Okay, well, welcome everyone. Welcome to this second in a series of 13 webinars on solar and battery design. It's basically an free online training course that covers the principles of how PV works and how to design a solar and battery system, whether it's on-grid or off-grid. We've got two of my fellow panelists here from Solar Plus. We've got Rachel and Laurie. What else affects the performance of a PV system? Well, an obvious one is shading. Now, what we've got here is a device known as a Solar Pathfinder. A Solar Pathfinder is a relatively cheap tool. It's no batteries included. It's just made of plastic. It's available from solarpathfinder.com. I'm not even getting any promotions from them, but I think it's such a great, useful tool for those who are working in areas, particularly where there's shade. Off-gridders would find this a very useful tool for siting and calculating the performance of a system. What you're looking at there is me looking down into the Solar Pathfinder and looking at the reflection of the shade items around the edges of that site. And there's time of day across the bottom, so you can see from right to left the time of day that the sun will be in certain positions, and then each of those arcs is a different month of the year. Now, it's probably hard to read it, but the bottom arc is December and it goes through to the top arc, which is June. And if you look carefully, you can see there's a whole lot of trees in the picture as well. The trees are obviously providing some unwanted shade on the solar system for this particular design. So it's a very useful tool for calculating the shading on a site. Now, you might not have a tool. You might have to just use some, seat of your pants calculations. Is it good or is it bad? Is it half shaded or not? But all of those are important factors when sizing a PV system. It's all very well to know what the theoretical peak sun hours. Remember, we covered that yesterday, the amount of energy falling per square meter from a PV system from the sun onto a PV system. But this allows us to derate that peak sun hours for the actual energy falling onto a surface. And so shade analysis is quite useful and I'd say very important where there is less than ideal sites. Now, I'm just going to glance over and check some questions have come in here. We've got, what else have we got here? From Benjamin, Glenn wants to know if you plan on running a course on solar install inspections. Indeed, in fact, Essential Energy have reached out to me and want me to run training. I was going to be going up there this month, or actually last month, to run some training for Essential Energy, but of course we're all in lockdown. So yes, I will be running some training courses. Like most of you watching this in Australia and New Zealand, probably or anywhere in the world, you've got a change to your life and your employment and you're locked down. So I'm personally trying to make the most of this situation by delivering training using the tools I have. So hence you're watching this webinar. Stephen asks, would a battery be classed as an upgrade to a system size isn't edited? The system size isn't edited or changed. Any considerations around whether you lose a feed-in tariff, where it's affected by things like adding a battery or not, really comes down to the regulations associated with your particular feed-in tariff. So I can't give a global answer or even a national answer to that one. You would check with your installer. They probably will be best informed about this for your particular system. But the logic is it doesn't actually increase the generating capacity, but there may be some other conditions around it, like the system is not modified in any way. And if you change an inverter, for instance, to add battery storage, that may be a consideration. So Jeff, hello Jeff. Yes, thank you. Paul Brownlee's asking, do we have a list of topics for each day? Actually, in the email, you would have seen 13 topics, and it's a rough guide. So today we are just finishing off the introduction from yesterday, then moving into a little bit on occupational health and safety. So finishing off on this, shade analysis is a very useful tool to have when designing a system where it's less than ideal. There are many tools available for this. Some of them as simple as an app. Personally, I use an app called Sunseeker on my phone. Really, it just tells you where the sun will be at different times of the day throughout the year, and you can uses the camera and the compass in your phone. It doesn't give you an energy calculation, but it just tells you position. So those are useful tools. Now we're going to move into a bit more technical area now, looking at how solar panels work electrically. So not too deep on the electrical theory here, just some basic principles about the operation of a solar panel or even a whole PV system. So what you're looking at here is what's known as a VI or IV curve, volts and current, I for current, V for voltage, of a solar panel. This is actually quite an old IV curve because solar panels these days put out a lot more current and a lot more volts than that one. But anyway, this is probably a panel from 15 years ago. Now the shape of that curve with a flat top, a knee, and then a sudden drop at the end is the performance characteristic over a range of voltage and current that the panel can operate at. Now panels are actually driven by the load that you connect to them. So a solar panel doesn't actually just push power out to your system. Your system, if it's an inverter or a charge controller, chooses how to operate your solar array. That's a very important point because it means that the charge controller or the inverter that the solar array is connected to can limit current, can limit voltage, or not really limit voltage very much, but it can limit current and can choose the power, therefore the power output of its conversion process. So an inverter or a charge controller is really a smart load. It's choosing how to operate your PV array. So let's go back to thinking about this diagram. What am I showing there? Well, I'm showing on one spot on that diagram the point at which maximum power is being reached. And this is only an 80-watt module. These days, that might be something you put on your RV, take camping with you. And it will only achieve that maximum power at one particular point on the curve where the sum of voltage and current give you the highest number. Now, it's up to your solar inverter or charge controller to find that operating point. And it's what's known as maximum power point tracking. It's something that is very, very useful in modern charge controllers. Old ones didn't used to do this. They used to just have a simple current limiting feature, but modern ones can actually track and adjust the input-output voltage. And solar inverters that connect to an AC output have to do this to operate over a range of power conditions. So what we'll see is the inverter will try and find that sweet spot on that curve by adjusting its input impedance and therefore adjusting the amount of current it draws and therefore modifying the voltage of the array until it sees the maximum power. Now this is not a static position. That point moves all the time. It looks like it's a static point, but it's affected by many things, including radiation levels, solar radiation levels. As the solar radiation levels decrease, so the curve flattens out. So you can probably see here, 1,000 watts per square meter, you might remember from yesterday, is typical of midday, clear, sunny day. That's kind of not an absolute maximum, but an approximate maximum. Some clouds come over or a little bit of haze, we drop to 800, and so the curve starts to flatten. 600 watts, it's now quite heavy haze. If you're getting a full clouded day, it's probably only 200 watts per square meter, and if it's raining, it might be down to 100 or less. So that curve changes because of irradiance. And as a result, the maximum power point moves around. So it's the job of the solar controller to find that spot. So we've got another question here from Richard. Richard says, how does the number of hours of sunlight shown in the Pathfinder correlate to the peak sun hours and derating for peak sun hours? Okay, so Richard, the Solar Pathfinder gives you, maybe I'll just jump back so you can see it. it gives you in each tiny segment, each half hour of the day, the percentage of the sun's energy. So it's probably pretty hard unless you've got a big screen or good eyes to read this, but around at the bottom curve, which is December, you'll see either side of the words December 7. And that means 7% in the period between 11:30 and 12, and 7% in the period from 12 to 12:30 of the day's energy is falling. And as it moves across to the afternoon, it's dropping 6%, 5%, 4%, etc. Those percentages can be summed. So if you know what the sum of the shading is, or the sum of the unshaded, you can then use that as a factor for derating the theoretical peak sun hours for that particular surface to the actual peak sun hours based on a seasonal or monthly figure. So it's very useful for doing quite detailed calculations. Question came and went there, didn't see it. There's a done, thank you. Good. All right, so going forward again, so back to IV curves and what affects them. The other big factor is temperature. Now, the temperature of a solar panel is generally detrimental to its output. So as it increases in temperature, its power levels decrease. And this is known as a temperature coefficient for power. And so different types of modules respond differently in terms of how much power loss. This is referred to usually as a percentage figure. So for instance, monocrystalline panels are tested, and all panels are tested at a standard cell temperature of 25 degrees Celsius. This is typically known as STC, standard test conditions. And those standard test conditions are 1,000 watts per square meter, a temperature of 25 degrees Celsius on the cell, and an air mass of 1.5. That's basically a sort of midday sort of color of the light. So air mass refers to the color of the light. For the monocrystalline panels, this figure varies from manufacturer to manufacturer slightly. So the lower that number, the better. And it might be these days around about negative 0.38% per degree Celsius. That means for every degree you go above 25, which is test conditions, you're losing 0.38% of your power. And for, say, polycrystalline, generally a little bit better, a little bit less temperature derating, so they're losing 0.35% for every degree you go above it. And of course, it's a linear relationship in the opposite direction as well. So if you live somewhere cold enough, and this is going to be a really cold place, that in the middle of a sunny day, the panels are cooler than 25 degrees. Now, you might think, oh, that's not going to be hard. It's 10 degrees here in Melbourne. Well, actually, no, you'd need to be about 0 or below in full sun to keep the cells below 25 degrees, because they heat up from the radiation of the sun quite quickly, a bit like a metal roof. So generally, you don't get much benefit from that temperature coefficient in the negative direction, below 25 degrees Celsius. But if you happen to live somewhere really cold, you will get more power than the panels are rated at. For thin film panels, we talked about those yesterday, things like technologies like amorphous silicon, CIGS, organic cells. There are a lot of technologies which fall under the umbrella term thin film, generally have very low temperature deratings, so 0.2% being typical for amorphous silicon. And that means they've got a little bit of an advantage, or actually quite a big advantage if you look at it, over crystalline in very hot conditions. I'd have to say that's probably not many places. Very hot being like daytime temperatures in the high 40s and low 50s. And, even though here in Melbourne, we might get to that a few days of the year in the middle of summer, it's not a big impact on the yield of a system over the whole year. It might be just a few hot days that you would see that significant derating with crystalline modules. So the term for that is coefficient, and you'll find it on the data sheets for modules. Now, the other thing that's temperature affects is voltage and current. Now, current, very little. I like to say almost insignificant variation in current due to temperature in terms of the design and operation of the system. But what is significant is the effect on voltage. the panel voltage changes significantly with temperature. So generally, as the panels heat up, and this is also reflected as a VOC, or voltage open circuit temperature coefficient, they drop in voltage. So as a panel heats up, its voltage drops away. So in this diagram you're looking at here, the panels at 0 degrees might be up around 24 volts. At 25 degrees Celsius, which is test conditions, might be around 22. But on a hot day, the panels may heat up to like 75 degrees Celsius, and so the voltage drops down to about 17 volts. So Chanyu has asked, ambient temperature or surface temperature? It's definitely cell temperature, so the temperature of the cell. The way to measure that, if you're ever trying to do it, is not from the front of a solar panel, but from the rear, which is the closest you can get to the actual cell is the back sheet at the rear, not the glass at the front. So using a thermal camera or a thermal non-contact thermometer, you can measure that, but you can also use thermocouples as permanently installed to monitor it if you're interested. Richard, are thin film cells such as amorphous silicon, CIGS, cadmium telluride more robust than conventional crystalline silicon, less prone to microcracking and other environmental transport impacts? Assume rooftop permanent installation. Every technology has its kind of niches, that you could say. Thin film, from my experience, is very much a niche product in areas like glazing, because you can actually make transparent panels out of them. You can make flexible panels, so they can be rolled up, like for camping. They can be made into wearables, so very small panels can be put onto cloth and materials. They can be embedded into appliances innocuously, like many calculators used to have a small amorphous silicon panel on them to power them without batteries. And as a result, being flexible often means that they're a bit more robust in terms of what's known as microcracking. But I wouldn't get too excited, Richard. It's pretty easy to damage a thin film panel by overflexing it. So camping panels that you roll up, for instance, if you crease them, that often ruins them as well. When they're installed on a rooftop installation, they might be much more stable, but there are other factors. There's degradation due to sunlight, varies with technology as well. So ironically, not all solar panels really excited about being in the sun. Some of the organic thin film modules actually degrade pretty quickly in the sun. We're looking at lifespans of like 2 years. So they'd be more suitable for disposable applications, maybe emergency sites that you just want to throw up a system and then dispose of it afterwards. Richard, John's asked, I live in the coldest town in Australia. Does this mean it's ideal for PV? I'm curious, John, what is the coldest town? I thought it was Perisher. I'm not sure if that's a town, but yes, the colder it is, the better performance you'll get instantaneously out of a PV system. But the problem is it's probably not going to be a lot of daylight sunlight hours. You're probably in a southern state, maybe Tasmania or somewhere, so your days will be shorter in winter. So actually, cold helps for instantaneous power, but we're generally more concerned about energy, which is the total amount of power times time. So that's probably not a big win for you. The app for checking solar window, Glenn mentioned. Well, there is a lot of them actually, but you know, this is not a promotion of these products. They don't pay me anything for this, but I just happen to have it on my phone, and I think it's called Sunseeker. Yeah, I'm looking at it now. There are a lot of them out there. If you just type in, you know, solar a site assessment or solar PV or solar app, you might find a range of them for both platforms, iOS and Android. Do some panels come with a cooling system for hotter areas? Sam, I wish I got $1 for every time I got asked that question. It definitely improves the performance of a solar PV system to cool it. Certainly, even in not such a hot area, just anywhere that the cells are over 25 degrees, you certainly will benefit from cooling them. But the cost of that cooling system is probably not justified, the maintenance and the extra hassle of installing a cooling system. So there's been a few efforts to do this. One nice way of cooling a solar panel, by the way, is just getting a hose and spraying it on it, but you're going to cost more on water usage than the benefit of power. Incidentally, this is a bit of a trick with some of the solar panel cleaning companies often say, look how much better your system is after we've cleaned it, while they're hosing it, and the panel power goes up and you get all excited and you take the hose away and the panels warm up and the power disappears again. Do some panels come with cooling? Oh, sorry, John's in Cooma. Yeah, it's a pretty cold place, Cooma, and it's sunny. Actually, Cooma would probably be pretty good. So, there's lots of design considerations in a PV system as well as temperature. So we looked at the effect of temperature on the voltage and power. Now I'm going to move on to, I should say one more thing about temperature as well, which is this is a consideration from an installer's perspective that the output voltage of a solar array will go above the nominal voltage of the panel as the panels are cooled. And that can happen on a cold winter's morning when the sun pops out from behind a cloud. So whenever you are writing on the compliance label for a solar PV system what the maximum open circuit voltage is, it's not just the nameplate rating on the back of the panels times the number of panels in series, which we'll get to in a second explaining what that is actually the temperature compensated maximum voltage. So you need to consider how much rise you get due to the coldest operating temperature of the cells. So Raj is asking Glenn, a fan to blow the hot air off the surface of the solar panels will be an option. Raj, probably true, yes, but actually just mounting panels on an incline provides quite good passive cooling. So being able to let convection do the work for you. But if you want to go to the effort of putting a fan on there, these are the kind of things that hobbyists and engineers like to play with. But many people just want something that's maintenance free, doesn't make any noise, and works for 20 years or so. So yes, you can squeeze a bit more out of a system, but the economics often don't add up. If you look at the cost of kind of making your panels colder versus the cost of adding one more panel, might turn out that you're actually better off just adding another panel and having no maintenance. So Jeremy, what about adding heat sinks? Yes, heat sinks certainly will help cool the panel, but heat sinks generally are expensive. If you've ever had to buy them for electronics projects, imagine putting that on the back of a solar panel. Interestingly, I was approached by a company who made emissive materials, and they were looking at putting emissive coatings on solar panels, and they wanted to test them here at my Smart Energy Lab. And emissive coatings, if you're not familiar with them, are things that are put on like re-entry crafts of spaceships to stop them overheating. They dissipate heat extremely well. They reject heat basically. But it turned out that the emissive coating would have cost more than the solar panel. It's very expensive stuff. So it didn't really fly, that idea. Jeremy, geez, how am I getting that coming through? Sorry about this. Jeremy's asking, hi, I got a new battery 2 days ago. I have 48 volt mustpower.can, whatever that is. You checked my settings. I went to blah, blah, blah. Jeremy, I think that's probably a little bit too technical for today. I might follow that one up with you. If you've got any questions that you want a more detailed response after this, put the comments into the comments field on my channel. So if you go to YouTube and you search for Smart Energy Lab, you'll find these webinars each day popping up. And I do moderate the comments, respond to the comments. And if you put some more complicated ones like that, Jeremy, I'll have a go at answering it. Justin's asked, the new battery standard ASNZS 5139, that's for New Zealand and Australia, protection devices required to have an IP rating of 56, no water. That's correct, Justin. I'm not sure what the question is there, but anyway, that is true. And Orb, do you have a link for a temperature effect calculator if one exists? Well, it's actually linear, so your calculator is the way to calculate it. So once you know what the temperature coefficient is for a panel. Now, I'm not brushing you off, Orb. I'm actually going to cover this in more detail with some diagrams explaining it in subsequent webinars. But you don't need any special tool other than pen and paper in your brain or pocket calculator. Bill's saying, if someone hosed a panel to help reduce temperature, what risk there is cracking the glass? Well, solar panels are pretty damn tough, actually, Bill. You probably know this yourself. You'd have to be hitting those panels to a tremendous temperature, well beyond their warranted, generally 70, 80 degree warranty, or more than that even, so to get the glass to be sensitive enough to crack. So I don't think it's a problem. I've never experienced it myself, and I've abused a lot of solar panels in many ways. They're surprisingly tough, by the way, like hail tests, etc., that they have to meet. What is the procedure for no water? Asked Justin. Justin, this once again is one of those questions that I prefer to answer in the comments on my YouTube channel. I am familiar with the test, so I'll point you towards the channel. This particular webinar will be up there later today. So, oh boy, the questions are great. Richard says, most thin film module data sheets show a low temperature coefficient, but only if the temperature range 25 to 75. Do you know why the minimum is 25? Well, that'll be a manufacturer's issue. They may actually not warrant the panel for very cold conditions. I'm not really sure what the answer to that one is. I would like to look more closely at the data sheets. Thin film is a broad range of products, including things like flexible panels, things which really aren't designed for permanent installations. So maybe they're not robust enough for really cold conditions. Jonathan asks, really hard to use those Pathfinders on a pitched roof. Yes, Jonathan, it is hard to use a Pathfinder with a tripod on a pitched roof, but here's my tip, is get yourself a small sandbag, or you can get these bean bags, or even just get a bag of rice, something that will mold to the surface of the roof, and sit the Pathfinder on that without the tripod. That works quite well. Sam says, some panels come with cooling systems in hotter areas, ? Generally no. Like I said before, it's probably not worth it. With all the fashion for black modules, has this had an effect in terms of their operating temperature? Just because it's black doesn't actually mean it's hotter. It can actually mean it's got a greater emissivity characteristic, so it may actually reject heat more effectively. I think that's a manufacturer's question. What is the effect on temperature on their particular module? Some people also ask, what about the roof? I've got a tile roof and that's going to be really hot, isn't it? And that's going to affect the panels. The panels, if you're attaching them onto an inclined tile roof, are going to shade the roof. So the tile roof isn't hot underneath the panels. So it's surprisingly not such a big issue. Just so many questions. How do I calculate energy loss for solar panels? Now, Pearl, once again, you've asked a question which I'm going to go into in much more depth in subsequent webinars. So I'm going to skip that one right now. And Yariv, g'day Yariv. I'm seeing some old friends here. Will you be talking about voltage rise calculations based on the examples in 4777 part 1? So you're referring to voltage rise on the output of an inverter. That won't be part of this series. This series will be more focused on the design around PV and battery storage. And inverter characteristics will come in subsequent webinars. Yariv, what you're giving me here is ideas. In fact, everyone is. And I'm excited by your questions, and I will weave them into subsequent webinars. So thanks, Yariv, but I'm going to dodge that one for the time being. And George, some discussion about sizing using bifacial modules. Now, George, I'm a bit of a bifacial virgin. I haven't had one yet. I'm apparently getting some shortly, so I'll get to test them in a very real way. They're actually going to go on a reference array with bifacial and monofacial of the same power rating under the same sun on a large tracking system. And we'll have some direct comparisons in a field of basically a grassy paddock here at the Smart Energy Lab. So one of the things I would say about them, George, is I'm learning about bifacials are a bit more complicated than you would think. I just assumed that a bifacial was basically as good as a monofacial, which means there's a back sheet on the back, so only light from the front can be useful, and therefore bifacial at least as good as a mono. But I'm told by the experts that actually that's not true, because there is a certain amount of bounce within a solar PV panel from the back sheet back into the module, into the cell, sorry. And so when you remove that back sheet in a bifacial module, unless you have some bounce coming back off the surface that's beneath it, like the roof, you may be worse off. So I guess I'll find out about that in practice, but just don't assume that bifacials are at least always as good as monofacials. Hey, Glenn, it says, Brody says, will you be covering batteries on today's topic? Not batteries today. Batteries are coming fast. But many of this kind of basic stuff applies to batteries. For instance, we're going to be talking about series and parallel circuits right now. So I'm going to pause the questions. You've been wonderful in asking lots of really good questions. So series and parallel circuits. Now, this is really basic stuff. If you're an electrician, apologies here. You would have done this in year one of your trade certificate. But for everyone, it's a little refresher with DC systems. What I've drawn here is symbol for a PV module is that rectangle with a little triangle on one end, and the letters PV to indicate it's a photovoltaic module. When you put photovoltaic modules in series, that means the output of one, the positive output of one, is connected to the negative of the next panel. You increase the voltage. So the voltage is summed, but the current passing through those modules is constant, not constant, is the same as one module. So you don't increase the amount of current, you increase the amount of voltage. So there's a little example here. And if you're looking at resistance paths within a circuit for impedance, you can do the same sums as well. So in many ways, a solar panel follows the same rules that resistive circuits do in terms of parallel and series. So voltage is summed in series, and the current stays the same as one module. Now let's contrast that with got one more slide, open circuit, no current, no load. So as soon as you disconnect a solar module, you'll have no current, but you'll still have voltage. It's an important safety consideration that so-called turning off a module by disconnecting it actually doesn't make it perfectly safe, because you've still got the voltage output at those terminals just waiting for something to touch them. So solar panels will produce voltage of near their open circuit voltage under a wide range of irradiance conditions. So even on an overcast day, when the panels are disconnected, they still have significant voltage on them. Parallel circuits are when you put panels connected the same poles together. So the positives are connected together, the negatives are connected together. And here I've shown a very simple parallel circuit where I've only got two panels. What happens here is the voltages stay the same. So it's known as Kirchhoff's voltage law. At that point where they join, the voltage has to be the same. So we've now got two panels in parallel. The voltage is the same in both panels, and the output of that system will be the voltage of one panel. But the current, we've got two sources of current now, and they join together at a common point. So we double the current. So parallel circuits, no change in voltage, but an increase in current with every parallel string. So some components in a parallel string is that the voltage is the same across all the branches, but the current is the sum of the combined strings within that system. And this is used particularly in small off-grid systems. You often will have quite a lot of parallel circuits, mainly because of historical limitations on charge controllers. They often didn't have a very high open circuit voltage or input voltage. And so, two or three panels in series was about the maximum you could put often on many of the DC coupled off-grid systems. And so we would see a lot of paralleling in a larger off-grid direct DC charging to a battery system. You can actually combine both of these, by the way. So here we've got parallel and series in one system. So we now got an array of 4 panels, and we've got 2 strings. A string is a series connection of modules, and those modules, 2 strings are in parallel. So now we've got twice the voltage, whoops, sorry, I jumped too fast, twice the voltage of one panel and twice the current of one panel by combining those. So using combinations of series and parallel allows you to hit the voltage requirements that you need to run a particular charge controller or inverter, and by paralleling to get the power levels up by increasing the current. Now, if we've got a system with quite a few strings, we can sometimes come up with a bit of a problem known as mismatched strings. Now, I just saw a question come in here from Jacody. What happens if we series connect panels, mono, poly, split cell, and different brands? Okay, yeah, an unusual situation. If you probably this diagram is a good one to explain the problem. In a series circuit, even though the voltages will sum together, so if you have different panels in one string, let's say you've got a panel that puts out 10 volts, a panel that puts out 20, and a panel that puts out 30, the sum will be 10 plus 20 plus 30, so 60 volts in that string. But the problem is that the current will be limited to that of the weakest link. So if you've got one panel in that string whose output is 2 amps, you will be limiting all of the panels to 2 amps. So you'll compromise the amount of power that they can produce. Therefore, it's generally a very bad idea to combine in one string panels of different technologies, such as mono and poly, and different power or current or current or power levels. But it is possible, and there are some products that allow this to happen. We'll talk about this in later webinars. I've been saying that a lot, but this is an introductory phase. We'll talk about module level power electronics and how they can be used to overcome some of these shortcomings. But I wanted to point out in this, I think this is our last 2 slides in this sequence, is that when you've got multiple strings, or even one string, and you get shading on a single panel, it will have an impact on that string and on the parallel strings connected to it. When you shade a panel, it will reduce its current. And like I said, the weakest link determines the current of all the panels in a series string. But we have a requirement that all PV modules have an inbuilt bypass diode, or diodes. There's generally multiple diodes in modern panels. And a bypass diode is there to protect against overheating due to partial shading. It also allows current to flow around a shaded panel and it not effectively crimp the output of that string. So I've shown one panel here in shade and it's now in bypass. When it's in bypass, it's not contributing to that string, so its voltage is not contributing. The current just goes around it through the diode. That will mean that there'll be a mismatch within the voltage of those parallel strings, and that mismatch will cause a performance drop across the whole array. So when you have multiple parallel strings, some consideration needs to be given to the likelihood of regular, significant localized shading, but a small amount, just, sun passes a chimney, or a chimney's not a good example. A tree might shade a panel for a half an hour in the morning, not a problem. And when you've got a significant amount of shading, it can take out the whole string as well. So the design of a system often is this is a consideration, is where shading might occur. So for instance, if you've got a roof that has shading on the eastern end, but none on the western end of a north-facing roof, you may choose to split the array into 2 strings, an eastern string and a western string, and connect them to separate controllers, so as to not compromise the whole array as soon as one part of that system is shaded. So we've got some more questions here. Gordon, thank you for your webinar series. Oh, thanks, Gordon. That's great. Those bypass diodes, are they the same as optimizers, asks Mishra. No, optimizers is a kind of industry term. More technically, in Australian and New Zealand standards, we refer to them as DC conditioning units. So anything that modifies sort of the voltage, current, and power of the input to the output is a DC conditioning unit. And those products like SolarEdge, Tego, Huawei make products that do this. They look like small packages, about 10 centimeters square, that attach to the back of a module, and you connect the module to each module level power electronics device or optimizer, and the output of those optimizers connect in series to other optimizers in the string. Now, this is something we will cover in a bit more detail in subsequent videos, but webinars. But I guess I'm saying is a bypass diode is a simple protection device. It's not something that will give you the maximum output of that system. It's really just there to help maintain its operation. Now, we've run out of questions. That's a bit of a surprise. Let me just pop out of this presentation now. And I'm back. There we go. So Bit of Q&A. We've got another 13 minutes, and I was going to move on to the next topic, but if you've got any more questions at this point before I change. Neil asks, are there any safety concerns with these differences in strings, or is it just performance? It is actually a requirement, and it's so therefore a safety consideration within our solar PV array standard 5033 for New Zealand and Australia, that when you have the potential in a multi-parallel string system for a fault in one string to cause the current in the non-faulty strings to overload that faulty string and basically thermally damage it, i.e., melt the insulation on the cables or panels, you are required to put in protection. Typically, that'll be a string fusing system or perhaps circuit breakers, but generally string fusing's used. Once again, this is something that's a bit more technical that I'd like to cover in subsequent webinars. So thanks for these great questions. You're just telling me what you really need to know. Chunyu asks, perhaps see lightning rods on Japanese house pictures yesterday. Is that necessary? Lightning protection systems vary from country to country. In Australia and New Zealand, our standards require us to do a risk assessment. And based on a risk assessment, covered in the lightning standard, tells you whether you need to put in a lightning protection system or not. In practice, that generally means in New Zealand and Australia, if you're not in an alpine region or if you're not in northern Australia, it's generally not required. But if you're up a high building, a mast, on a tall steel structure, that may definitely be a requirement. So that's really just a risk assessment. Lightning is pretty hard to stop too. So even with a lightning protection system, you still may fail. Peter asks, were the half-cut solar cells designed to assist with potential shading issues? Yes, Peter. Half-cut cells, if you're not familiar with them, they're a bit of a new thing in the last few years on the market, where the cells, instead of being a typically square cell, they're cut it down the middle, and you end up with two rectangular cells, and they're wired into two subarrays within a module and two submodule components. The benefits of what's so-called split cell modules is more shade tolerance, because you've got more opportunities to bypass localized shading. You also get a lower current through the cells, and therefore, if you're familiar with the formula for power, I squared R, reducing the current has a cube relationship, square relationship on the change in power levels. So a small improvement in reducing resistance has a big improvement in increasing power. So half-cut cells have become quite popular. I asked one PV manufacturer why they didn't do them years ago. It seems pretty straightforward. And they said, well, actually, it was really hard to cut them and not fracture them. So the technology was holding us back to efficiently cut them and reliably mount them without any faults. Richard also asked, are thin film modules considered a single cell? And so is a single bypass diode required per module? Generally, thin film modules, because if you're talking, say, amorphous silicon, for instance, are manufactured in situ on the glass they're attached to, they actually etch in the bypass diodes as part of that manufacturing process. So they often have a bypass diode for every cell, not just every collection of cells. So very, very shade tolerant. Amishra asked, how come there is no circuit protection between the arrays and the inverter? So in a grid tie system, or grid connect, depending on what you refer to it as, where you have a PV system connected to a device that converts DC to AC and directly supplies the grid, we're not talking about a battery system here, directly to the grid. It's a one-way conversion device. That means it'll only take DC and make AC. It can't reverse that process. The other thing to consider is that a solar PV array is a current limited source. Its maximum current is defined by the module. So if the module says it can put out 10 amps, it can't put out more than 10 amps. So if you try to put any circuit protection on that cable that goes from the PV module to the inverter, it's not going to do anything. It's never going to trip. If it does trip, it'll be nuisance tripping, and it's not necessary, because if you know what the maximum current is, your cable selection for your solar array is your overcurrent protection. So that's why with grid tie systems, overcurrent protection is not required on the array. It's only when you have the potential for backfeed, and that's when a battery DC coupled to an array is definitely a source of backfeed. Greg asks, What's the best way to bring lead acid battery bank up to the latest standard with regards to fusing protection? Wow, Greg, that's going to take quite a bit to answer. I think I'd even need pictures. Yes, the new battery standard is it's quite complex to dive into straight off. I will be doing, once again, a webinar series looking at battery safety, and that will cover the new battery standard. So, Greg, watch this space. Peter asks, multiple roof areas where panels cannot be installed in one roof area. Would the series and parallel configuration be a possibility to cover the general supply to a home? Yes, Peter, that's actually become a very popular design philosophy, is to use multiple parts of your roof to cover generation over a larger period of the day, rather than just have all of your panels facing in one direction. It's where you need to understand the characteristics of the load that you're trying to supply. We will look at in more detail at design software for designing a PV system and battery storage as well, and take into consideration the relationship between load and location of arrays and size of arrays. So actually having load data is really useful when you're designing a PV battery system, and it will give you information about, for instance, is east and west arrays better than, say, a north array. Mark asks, will an inverter cut out on over voltage or simply limit allowing a longer generation at a higher power? Mark, this is a manufacturer's issue. The manufacturer says maximum input voltage 600. They mean 600. So if the inverter protects itself in any way, that's a bonus. From practical experience, it often doesn't protect much more than the maximum. So generally, with a grid tie inverter, the PV arrays are connected across the input capacitors, and they might have a 600 volt maximum rating, and you go to 620 volts, and the dielectric breaks down and they blow up. So generally, it's a very bad thing to exceed the manufacturer's recommendation. Christoph, can you recommend any device to get your solar grid generating during a blackout without installing batteries? I thought this was impossible a few years back, or in fact quite a few years back, until a couple of products appeared on the market which actually would work without batteries. It's a dubious benefit though, because as soon as a cloud comes over, the output might disappear. So if you're happy to have a house that the lights go on and off whenever a cloud comes over, there are such systems available. In fact, they're often a sort of accidental feature of some DC coupled hybrid inverters. But I wouldn't get too excited about them, Christoph. I'd still want to put in a small battery as part of that. Ofer, what's the highest voltage from panel can cause electrocution? Actually, Ofer, it's current that kills you. And this is probably quite a good segue to the safety subject that we probably run out of time to talk about today. But just to kind of give you a very brief answer, generally DC at the similar voltage levels is more dangerous than AC. And the reason for that is an alternating current passes through 0 volts like 100 times a second, or depending on what your frequency is. And so it's basically quenching itself. Any arc that occurs, it quenches 100 times a second. But DC doesn't go to 0 volts, it just stays there. And so if you get a shock from a significantly high DC voltage, 100 or 200 volts will do it, it will burn your skin, it will create a better conductive connection to your body. And if that is across a vital organ, like your heart, it's not fibrillation that you worry about, it's actually burns, internal burns to muscle tissue, and so is more likely to be fatal at similar voltage levels. So I guess this is just a safety message before I get on to actually talking about it in more detail. But DC can be more dangerous than AC at similar voltage levels, and that's why we have licensing requirements when installing electrical systems. So in Australia and New Zealand, you need to be a licensed electrician if you're working on systems that are over 120 volts DC or 50 volts AC. Yuriv says, another potential item discussed in coming webinars is AI and drone technology. Oh, you're a man after my own heart. I do love a drone. So yes, we will actually give some demonstrations of how you can use drone imagery in design. Thomas, and we are winding up now. We've got 3 minutes to go. Hey, Glenn, thank you for taking the time to talk to us. Can you discuss off-grid switchboard discrimination in your seminars? Okay, I'll add that to my wish list. Great, really, really good. Now, because we've virtually run out of time, I'm just going to touch on the beginnings of the next slideshow. So let me just bring that up. What you're looking at here is the beginning of the meat of this webinar series, which is looking at in more detail at design and selection for off-grid and also for hybrid. So I cover both topics actually. Just to kind of give you a little bit of an overview of why batteries are becoming very popular on-grid as a contrast to off-grid where they've been essential forever. The Solar Council, now called the Smart Energy Council, did a survey back in May 2017. They might have done subsequent ones, but this is the one I had access to, which they published. And it's really interesting that people are choosing battery storage on-grid very strongly for reasons like energy independence. Now, what does that mean to people? The solar energy is mine. I want to use it myself. They want to save money. Now, just because you want to do something doesn't necessarily mean it's true. So whether it's true or not is another question. And you'll see that backup is a very big part of that motivating force. So to be able to have power when the grid fails, and also producing your own clean energy and for other reasons. Now, we've actually reached 12 o'clock, which is when this seminar series winds up. What I'd like to say in sort of just closing off for today is a lot of great questions came. I'll be reviewing some of those. So please encourage you to comment in my channel on YouTube, Smart Energy Lab, and I'll answer them in more detail. Also, this session, which has been recorded, will be uploaded to YouTube later today, and you'll be able to share it with others and view it if you missed part of today's presentation. And today is day 2 of a 13-part series where we'll go right through the whole design process of a solar and battery storage system. I'd like to thank my panelists who have been quietly working away in the background, making this run a bit smoothly, which is Rachel and Laurie from Solar Plus. Rachel and Laurie and I and others work in a field of designing software for designing solar PV systems. So we'll actually get on to talking about using software in subsequent webinars. So thank you, everyone. Thank you very much for attending. And I hope to see you tomorrow, same place, same time, same channel, as they say. Thank you. Thanks for watching today's webinar. And tomorrow we'll dive deep into system configurations for hybrid and off-grid systems. See you then.